Daniel Gibson and his collaborators at the J. Craig Venter Institute have made the first synthetic cells. Each cell's entire genome was edited on the computer, assembled by machines and helper cells, and finally transplanted into recipient cells. Technology Review selected synthetic cells as one of our 10 emerging technologies of 2011. The innovative techniques used to make the first synthetic cells will expand the possibilities of biological engineering and lead to advances in making vaccines, as well as making it easier to redesign cells to produce biofuels, drugs, and other useful chemicals. Gibson, an associate professor at the Venter Institute, explains that the group's original motivation was to make what they call a minimal cell.
I'm Dan Gibson. I'm an associate professor in the synthetic biology group at JCVI. And the ultimate objective of our synthetic biology group at JCVI is to synthesize a cell that has only the machinery necessary for independent life. And this is an idea that was conceived more than 15 years ago by Craig Venter, Ham Smith, and Clyde Hutchison. And this was shortly after the sequence of Mycoplasma genitalium was deciphered. And this organism has a very small genome of only 583 kb, and it's thought to have the smallest genome of any organism that can replicate and grow independently in the lab. And so the idea was, since it's close enough to a minimal genome already, maybe we could make a minimal cell by synthesizing the genome and activating it. And so if we could understand all of the genes necessary to run the machinery of a cell, then this would really help us understand the biology of a cell. And maybe by having a minimal cell, this genome of the minimal cell could be used as a launching pad for making more complex and useful organisms. Also, if we were to make a minimal cell, maybe this would help us understand how to design synthetic cells that had some very extraordinary properties, like sequestering carbon dioxide, producing biofuels, industrial compounds, and antibiotics. When we began this work in earnest in 2004, synthesizing a complete bacterial genome didn't seem like a very easy thing to do, because the only completely synthetic genomes were viral ones, and these are very small pieces of DNA that are only 5 kb or so. And the largest stretch of DNA, of synthetic DNA, that was reported in the literature was only 32 kb. And so the genome that we wanted to synthesize was 583 kb, which was about 18 times larger than any piece of DNA that has ever been synthesized before.
Gibson's group started with the sequence for a very small genome from a Mycoplasma bacterium. But even after they edited the sequence on the computer to delete some genes that were unnecessary, the genome was a piece of DNA much larger than any that had been made before. Gibson's innovation was to use DNA synthesis machines to generate a sequence in 1,100 small fragments, then rely on yeast cells to stitch these fragments together, 10 pieces at a time, until the complete genome was assembled. He then transplanted the genome into closely related recipient cells to prove that the process worked.
Now that we are able to make synthetic cells, this gives us complete control over every single nucleotide of that genome. And so now we have the ability to engineer these genomes to produce cells that have some very extraordinary properties. Along the way, we've gotten very good at rapidly synthesizing fragments of DNA.
The nonprofit Venter Institute is now working with the company Synthetic Genomics to apply Gibson's work on DNA assembly to the problem of making flu vaccines more rapidly. Vaccine technologies that can keep up with the rapidly mutating virus could save lives. Gibson is also continuing to work on creating the minimal cell.